Now we're going to talk about cell potential and delta G. So we've set up our idea of what an electrochemical cell is, what the parts of the electrochemical cell are, the flow of electrons, the notation to describe electrochemical cells, all of those ideas. And now we want to talk a little more context about some of the ways we can predict or what kind of drives the cells. So electromotive force is the tendency of electrons to flow between the electrodes of our cells. So electro, that's electrons, motive is motion, and force is driving factor, or some sort of what makes it happen. And so electromotive force is a measurement of basically that flow of electrons from your anode to your cathode through those wires. We quantify that with what's called the cell potential. And our symbol for that is going to be a capital E with cell as a subscript. So E cell is going to be the cell potential. We measure this in volts, so voltage, if you're familiar with electricity, if you're familiar with electricity. So we measure this in volts. And 1 volt is 1 joule per coulomb. So a coulomb is a unit of charge. Now we'll see, it's just a measurement of how much charge. So electrons are charged. A mole of electrons is this many coulombs. So it's just a measurement of kind of how much charge is going through. And so volts are really a measure of energy per charge. So in some ways, it's a measure of energy per electron that flows. So this is going to be related to the chemistry that drives it. Basically, because when that electron is flowing from the anode to the cathode, it's enabling a chemical reaction to occur. And this is a measurement of basically how much energy is associated with that flow of electrons. Is it really high? Is there a really big push for electrons, or is it much weaker? So because this is all related to the chemistry that's underlying the process, the E cell is related to the delta G of that redox reaction. Okay, so our equation is going to be delta G is equal to negative NF E cell. So we can see E cell is the potential of the cell, basically how much those electrons are being pushed, how bright they can make that bulb in a way. And it's going to be related to basically how spontaneous is the underlying chemistry. Does the chemical reaction really, really want to happen or not? And so we have these other two terms in here then, N and F. N is the moles of electron transferred in the reaction. So when we did all that balancing stuff, the idea that some number of electrons come out of the the oxidation step and they go into the reduction step. So balancing that flow of electrons, that number of electrons, that's N. F is a constant. It's Faraday's constant. Michael Faraday did a lot of work with understanding electricity, and Faraday's constant gives us the charge of 1 mole of electrons. So 9.65 times 10 to the 4th coulombs per mole. So that's it. That is the kind of charge of a mole of electrons. So it is technically coulombs per mole, but if you remember, 1 volt was 1 joule per coulomb. So it is really common that instead of seeing it written as coulombs per mole, it's joules per volt mole, where basically you're just using the relationship between coulombs and joules and volts, that relationship between all those units. So let's apply this, let's see it in action. So for the reaction, copper plus silver cations gives us copper 2 plus silver. Hey, this was a reaction we've seen previously. E cell is equal to 0.46 volts. What is the delta G for this reaction? All right, so we got our reaction. We know what E cell is. We want to know what is delta G for this reaction. So when we're given E cell, that's a good sign we're dealing with electrochemistry. We can see we have reactions where ions are changing from being ions to not. Another good sign we're dealing with electrochemistry going on here. And if we want to know the delta G for when we're dealing with that, delta G is going to be negative NF E cell. So we want delta G. So the question is, do I have all of these other variables? Do I know N, F, and E cell? Okay, so one of the things that E cell, you can see is 0.46, we're good on that. This is Faraday's constant. So this is a constant number, always 9.65 times 10 to the 4th coulombs per mole. So the question is, what's N? And so this N comes from balancing. So it comes from figuring out what is the transfer of electrons between the half reactions. So we need to pair them up, copper to copper, silver to silver. It's one we've seen before, but we'll go ahead and work it out. Copper solid becomes copper 2 plus, silver plus becomes silver solid. So we know here we're going to need the 2 electrons. Here we would only need 1 electron. But right, this is the kind of case where we would say, well, we need 2 times here because we want the 2 electrons to match up the 2 electrons. So because it's a 2 electron transfer, that means N is equal to 2. And it would be whatever it is for that particular reaction. So we plug in the 2, 10 to the 4th coulombs per mole times 0.46 volts. So we can do the arithmetic. We get G is negative 8.88 times 10 to the 4th coulombs times volts per mole. So the first issue we're going to need to deal with here is this coulombs volts. And what we can return to is the fact that 1 volt is 1 joule per coulomb, which means we can rearrange this. 1 volt times 1 coulomb is 1 joule. And that's just basically 1 volt times coulomb is equal to 1 joule. So we can basically plug that in right there and end up with delta G is negative 8.88 times 10 to the 4th joules per mole. So this would be an answer. We've seen this before. And joules per mole is totally fine for delta G. We wouldn't want to leave it as coulombs times volts. That's kind of it is a unit, but it's not that meaningful. When we've talked about Gibbs free energy before, it's always been joules per mole or kilojoules per mole. So what we also want to do is kind of take this and rearrange it. So what we'll do is we'll write this. We want to get it into kilojoules. So we could go from scientific notation into full notation. So that's at 88,800 joules per mole. And so that would be negative 88.8 kilojoules per mole. So one of the things that we can see right away in terms of comparing these ideas is that delta G is negative here. So this is delta G less than 0, and that's spontaneous. So it's going to be the same thing for E cell, but it's the opposite, because here our E cell was the positive 0.46. So E cell greater than 0 leads to it also being spontaneous. So those two things are the same. And basically what this implies is that Gibbs free energy directly informs, is directly related to E cell. That they both are talking about, does the reaction spontaneously happen? Is there a push for electrons to flow? But those are really the same thing, because electrons are flowing because the chemistry is happening. So we can use this relationship to just go back and forth between these two basically representations. One's that's explicitly looking at the chemistry, and one that's more focused on the electricity applications or pushing electrons, using electrons to do things, light up light bulbs, play stereos, start a car, whatever it may be. So with this delta G being negative, we know that the reaction is spontaneous. That is consistent with getting an E cell that is positive. Right? There is a push, there is a energy gain per electron. This is the amount of driving force for the electrons. And as the delta G would become more negative, we would think the reaction is becoming more and more spontaneous. The reaction tends to happen more and more, and we would expect to get a bigger drive for electrons to flow. So if we choose different chemical reactions, we can have stronger spontaneity that can correspond to stronger potential, which means more force of electrons moving, more tendency for electrons to flow, more driving force. And so we can tune the chemistry that we're using to how much kind of voltage, how much power, or not power, sorry, voltage or potential is coming out of our cell to kind of get more work out of it, to make our light bulb burn brighter or glow brighter, that kind of stuff. All right, first video done for this set. We're looking for questions on participation 1111. Nothing yet, nothing in this first video, but we're just getting started. Week 12 homework will be due Wednesday covering this material, and then microvoltaic cells lab will be on Wednesday. You're gonna actually make cells. It's pretty cool. I like this lab a lot. You can just do electrochemistry, measure voltages and see all sorts of stuff. It's very cool, very cool. If you have any questions about anything, let me know. Otherwise, welcome to week 12, the second half of chapter 17. It's going to be all about cells all week, so I hope you're enjoying it. See you in the next video.